Greetings, my name is Ron Darnell. In this presentation, we'll explore R&D for robotics in manufacturing. We'll focus on four key R&D areas: autonomy, human-robot interaction, multi-robot coordination, and reinforcement learning. Adaptive autonomy, known as Autonomy 2.0, technologies are drivers of Industry 5.0 in manufacturing. Autonomy is now the driving force in modern manufacturing. Robots can self-manage their actions, shifting seamlessly among manual control, shared control, and full autonomy based on real-time sensor feedback and operator cues. This adaptive autonomy, which keeps a human in the loop while allowing machines to tune their behavior, is the cornerstone of the Autonomy 2.0 roadmap, where data-driven systems self-tune and scale rapidly across multiple factory sites. Industry 4.0, which began in the mid-2010s, laid the groundwork by networking machines and harnessing advanced analytics to optimize processes and predict maintenance needs. Now, with Industry 5.0, which builds upon that by adding resilience and true human-robot symbiosis. Robots just don't follow scripts. They learn and adapt to changing conditions and operator needs. By continuously refining control parameters and workflows, Autonomy 2.0 frameworks half development time and cut engineering efforts, paving the way for agile human-centered factories. Next, we'll quantify how Autonomy 2.0 inspired frameworks result in productivity gains in development time and engineering effort. Human-centered autonomy frameworks half engineering time and development effort. Wu and colleagues, 2023, show that traditional script-centric systems typically demand around 1,200 engineering hours and nearly 20 weeks just to get a single production cell running. In contrast, an Autonomy 2.0 framework built on modular autonomy components cuts that engineering effort in half to about 600 hours and slashes deployment time down to about 8 weeks. How does this happen? Well, operators can tweak autonomy parameters on the fly through intuitive tools instead of rewriting code for each new task. That immediate feedback not only speeds tuning, but also builds operator trust, reinforcing human-robot symbiosis. In other words, adaptive autonomy delivers true economies of scale, where factories can roll out resilient, human-centered systems more quickly and at lower cost. So next we'll turn our attention to the human-robot interactions that makes these systems so effective. Effective human-robot collaboration hinges on intuitive interfaces and AI-driven perception systems. When robots fully collaborate with people, they need more than basic programming. They must understand and respond to our actions in real time. Modern perception algorithms, for example, let robots recognize human gestures, voice commands, and even posture shifts on the fly, as demonstrated by Salinas Martinez, 2023. Paired with intuitive drag and drop or touchscreen interfaces, this capability enables seamless, hands-off, and synchronized motion, so a worker can guide a robot's precision task, such as inserting a delicate component without a single line of code. This hybrid model of human-in-the-loop interaction not only preserves human oversight for high-level decisions, but also lets robots efficiently handle repetitive, precision-based work. The result is a significant boost in throughput and flexibility. Robots shoulder the heavy lifting, while humans focus on strategy and quality, creating a truly collaborative manufacturing environment. We'll take a look at human-robot interaction and efficiency gains next. This chart highlights two critical benefits of AI-assisted human-robot interfaces in manufacturing. First, throughput jumps from about 50 units per hour with manual interface to 70 units per hour when operators leverage AI programming and perception. A 40% increase that means dramatically more parts are produced each shift without adding headcount. Second, the activation of AI safety zone cuts collision and risk events from a baseline of 1.0 down to 0.4, which is a 60% reduction in near misses or stoppages. Together, these improvements translate into higher capacity, fewer unplanned shutdowns, and lower maintenance costs, demonstrating that intuitive AI interfaces not only boost productivity, but also protect workers and equipment. Next, we'll see how these same principles enable multiple robots to coordinate seamlessly for even greater efficiency. Robotic arms can share state and negotiate tasks to assemble products efficiently and safely. These schematics here illustrate a modern robot assembly cell where multiple arms collaborate on a single product. In this system, each robot continuously broadcasts its state, ready for action, and its specialized capability, whether that's screwing, welding, or placing components. By sharing this information in real time, robots know which peer is best suited for each task. If one arm recognizes a neighbor is closer or better equipped, it instantly negotiates a task handoff, keeping the line flowing with no idle gaps. Simultaneously, adaptive safety bubbles around each arm. If those bubbles threaten to overlap, the system automatically pauses or reroutes motion to prevent collisions. According to Dewan et al., this decentralized approach not only boosts throughput by cutting wait times, but also maximizes safety, all without relying on a central controller. Finally, we'll see how reinforcement learning can further refine these coordination policies to handle new products and unexpected disturbances. Adaptive reinforcement learning enables robots to rapidly master assembly tasks. Adaptive reinforcement learning, or RL, lets robots learn assembly skills much like humans do, by trial and error. In today's manufacturing, we've first trained deep control policies in high-fidelity simulators, as Zhu et al. Describe in their sim-to-real pipeline. Through domain randomization and adaptation, these policies bridge the gap between virtual and physical environments, then require only a handful of real-world trials to fine-tune performance on the shop floor. This approach dramatically cuts manual programming. Instead of handcrafting every motion, engineers define reward functions and let the robot discover optimal behaviors. The roots of this method go back decades. Yang and Asada in 1993 showed that in a ball alignment task, a robot starting with basic position control could learn force feedback gains over hundreds of trials, achieving significant performance gains. After just 100 attempts, combining fast and safe learning and simulation with focused real-world tuning, adaptive RL empowers robots to rapidly master new assembly tasks, handle part variations, and improve resilience to set up hours, transforming how we deploy and scale robotic systems in modern factories. Thank you. In this presentation, we discussed autonomy and human-robot interaction, multi-robot coordination, and reinforcement learning as topics of R&D in manufacturing, robots in manufacturing.